So in this video, we're going to look at substitution, which uses essentially the reverse chain rule, the chain rule from differentiation in reverse. You've seen it in the advanced course, and you've also seen it in the extension 1 course. What makes things different for us a little bit is that we're often not told what the substitution is, when we might not even be told it's substitution at all. We need to work out that that's the appropriate technique to use. If we are given a substitution, we can be pretty confident then that means we're going to have to do a fair bit of work before we get to the integration step. If you need a refresher on the reverse chain rule, you can see it up here now, going through and proving how it works. But essentially, we're going to have to find some function u in terms of x and its derivative, and that'll help us transform the integral into something that looks like a standard form integral, and we'll be able to solve the problem. So here's a first example. We've got the integral of x squared over the square root of x cubed plus 1 dx. Now I generally look for where are the issues, where's the thing that's causing the problems, and it's that denominator, the square root of x cubed plus 1. So that's where I'm going to direct my attention and try and find an appropriate substitution. So if I let u equal x cubed plus 1, and then I take the derivative, then I get du dx equals 3x squared, and with a little bit of rearrangement, I get 1/3 du equals x squared dx, which is nice because that's the numerator. And that's where this technique becomes really nice and powerful. If you look, then it has caused a nice simplification of the integral. It's now a stock standard integral that we can solve. And the final step is what we call back substitution, where we go back from u and replace it with x. In this second example, you can see we have a definite integral. It's running from 0 to a half, and we have sine x over 1 plus cos x all cubed dx. So here we're not going to have to do some back substitution, but what we will need to do is use u, plug in some x values, and find out what the equivalent u value is, and that's how we're going to change our limits. So no back substitution, but we do have to adjust our limits. Now again, looking for the problem, it's that cube on the bottom. So I'm going to let u equal 1 plus cos x, and the derivative du dx becomes negative sine x, which means that du is equal to, or negative du is equal to sine x dx. Again, that's the numerator, so this problem collapses down nicely. We've adjusted the limits appropriately. So when x is 0, u is 2, and when x is pi on 2, u is 1. But as you can see, at the moment, the limits are running backwards, the bigger numbers on the bottom. But hopefully you remember from your advanced and extension 1, if that happens, if the limits are the wrong way around, then we can flip them. We've just got to take the negative of the integrand, as you can see here. Again, now this is a really simple problem to solve, and we get a solution. We don't have to back substitute, as I said, because we just get a numeric answer that pops out. So in this example, you can see we are given a substitution. We're told that u equals the square root of x, and we're looking at the integral 1 over x plus root x. And in fact, it's going to be easier if we work with u squared equals x, as you'll see. The problem with that is what we've done now, we've got a implicit definition here rather than an explicit definition. So we're going to have to use something called implicit differentiation. And it's going to be nice and easy. It's basically the chain rule again. Because what you can see is we want to take the derivative, d dx of u squared equals d dx of x. That part's just 1, that's easy. But we can't find d dx of u squared because u's the wrong variable. What we want is d du of u squared. And in fact, if I multiplied that by du dx, then it would collapse down to the thing we've got, d dx of u squared. So that's how we're going to attack it. We're going to replace d dx of u squared with d du of u squared, but we're going to multiply by du dx. And the derivative of u squared is just 2u, so we get 2u du dx equals 1, and then with a little bit of rearrangement, we get that 2u du equals dx. And you can see now that that integral collapses down really nicely, and we can solve the problem. So in this example here, you can see we've got a definite integral, and an implicit definition here is going to help us for u. But what we're going to see is, because we've got to evaluate these limits, we're going to have to take the inverse function, and we want to make sure it actually is defined, that we don't run into any problems where it's undefined. And you'll see that happening as we work through the problem. So the first thing I notice is that there is a difference of squares underneath the square root. That should be jogging your memory, and you're thinking that's a semicircle. It's the upper semicircle with a radius of 2. So it would make sense, hopefully, that we're going to use a trig substitution. And a good trig substitution here is going to be that x equals 2 sine theta in terms of that radius. But we're going to restrict the domain for theta to be between negative pi and 2 and pi and 2. And the reason we do that is when we take the inverse, then we know the inverse sign is going to be defined. And it has another nice consequence. Cos x is going to be positive. So now we can easily take the derivative. If I do dx to theta, then I get 2 cos theta, and therefore dx equals 2 cos theta to theta. Plugging in x equals 0, I get theta equals 0. Plugging in x equals 1, I get theta equals pi and 6. So they're my two limits. And when I plug all that into my integral, then it rearranges, as you can see over here. Now, the first thing I notice is that there's a common factor of 4 underneath that square root. So when I pull it out, it's going to become a 2. And that's where that 4 cos theta comes in. I'm then left with a 1 minus sine squared theta underneath the square root. I can use my Pythagorean result and get cos squared theta. Now's the potential drama. The square root of cos squared theta, we should recognize that's the absolute value of cos theta. So we've got a potential issue here that we could have a positive or negative answer going in here, but that's where our earlier restriction came in to save us. We know cos theta has to be positive here. So we just get 4 cos squared theta. As is, we still can't solve this integral. But here comes some extension 1 to help us out. We can rewrite cos squared theta in terms of cos 2 theta, and the problem just collapses and we can solve the problem. So to summarize, when you're working with substitutions, the reverse chain rule, concentrate on the area that's causing dramas and try and use that to create your substitution U. Try and use an explicit substitution rather than an implicit. If you do have to use an implicit substitution, then be aware that you might have to restrict domains. So if you need to take inverse functions, they're going to actually be defined.